चलिए स्टार्ट करते हैं आज का लेक्चर विच इज़ वेरी इंपॉर्टेंट लेक्चर। सो प्रीवियस स्टडी में हमने ये देख लिया था कि एक सर्कुलर पाइप है अगर, तो उसमें वेलोसिटी का क्या पैटर्न होता है। ठीक है, सो वी हैव स्टडीड दैट व्हाट इज़ द पैटर्न ऑफ वेलोसिटी in the previous study. So now we will going to see the different cases when the velocity is maximum, when the velocity is zero. So all these things we are going to discuss. So what is the relation? So first, what is the relation? So we are going to see. So relation is u minus 1 upon 4 mu del p by del x r square minus small r square, and the velocity is maximum. Velocity is maximum. Suppose this is the pipe, this is the pipe, this is the pipe, this is the pipe, and velocity is maximum at the center. Here the velocity is 0, here the velocity is 0, and here velocity is maximum. So from here to here velocity decrease gradually, and here, so if you draw the velocity profile here, velocity profile will look like this. Here the velocity is maximum and velocity continuously decrease, and it will eventually become 0 at the wall of the pipe. So if we take the radius, small r, so here small r is equal to 0, and here small r is equal to capital R. So at the wall small r is equal to capital R, and at the center small r is equal to 0. So if you want to find the maximum velocity, Umax, it must be at the center. That means small r is equal to 0. That results into minus 1 upon 4 mu del p by del x capital R square. So this is the maximum velocity. Of course, at the wall velocity will be 0, so minimum will be the 0. So if you want to find you can say ratio of maximum and velocity, so u by u max, that will be capital R square minus small r square upon r square, which results in 1 minus small r square upon capital R square. So that is the thing. Now we are going to calculate discharge or Q. What is the Q? What is the discharge in the pipe? So for the discharge you need to know one thing. Discharge can be calculated by the average velocity in the pipe. So the velocity is changing from here to here, but anyhow if you calculate the average velocity and then you multiply the cross sectional area of the pipe, you will get the discharge. Okay, at the same time you can integrate the velocity with respect to the cross sectional area, and then also you can get the what you call uh, discharge. So suppose here is the small element. Here I'm taking a small element inside the pipe, and here I'm assuming the velocity is constant, that is u, and the radius is small r. So the radius is small r. So what will be the you can say what will be the area? What will be the area? What will be the discharge? Discharge is u into what is this area? What is this area? What is this area? So if you take this small area through which the flow is passing, so suppose I am just making the exploded view so that it is more clear to you. So what actually I'm doing, let us take a small element of the fluid. Let us take a small element of the fluid, and from here to here this radius is r, and this is dr, and this is dr. So fluid here, suppose the velocity is u. In this section the velocity, this is a very small section dr, this is velocity is u. So if you want to calculate what is the area, this area, so this area will be 2 pi r dr. This area will be 2 pi r dr. If you see from here, it will be more clear. Cross section, this is the r, and you are calculating here what is the velocity. So you are assuming from here to here velocity is constant, that is u, and this gap is dr gap. So what is this area? This area will be 2 pi r dr. Okay. So now you have to extend this dr from r is equal to 0 to r is equal to capital R. So you have to integrate this from r is equal to 0 to capital R. So this is the discharge. And what is the u? What is the u? So u is equal to u max, that is a constant. U is equal to u max, and you can say 0 to r, 1 minus small r square capital R square. 2 pi r dr. So q is equal to u max 0 to capital R 1 minus small r square divided by capital R square r dr. You can take 2 pi also here, 2 pi. So if you going to integrate it, so you will get 2 pi u max and this will be r, so r square by 2, and this will be r cube, that means r to the power 4 by 4 r square 0 to r. If you put the limit, then you will get r square by 2 minus r square by 4. So from here you can get 2 pi u max, this is r square by 4, this is r square by 4, and here you can see pi u max r square by 2. This is the q, this is the q. So you will get the relation q is equal to pi u max r square by 2. So this is, similarly you can also define q by u average into pi r square. So if you see what is the relation between the u average and u max, so you will get for the pipe u average by u max is equal to half. And what is the relation between u and u max? It will be, what is the relation between the u and u max? It will be 1 minus small r square by capital R square. So I think you are very clear about that. So if you want to get the relation between u and u average, so what you have to do, it will be 2 into 1 minus small r square by capital R square. Simply you have to put this value here. In the place of u max you have to put 2u average and you will get this result. So this is the relation, and this is the, and another thing, if you want to calculate q from the pressure drop equation, then simply you have to put the value. So q is equal to pi u max r square upon 2. Is it correct? Yes. So what is the u max? Minus of del p by del x, minus of del p by del x, r square by 4 mu, 1 by 4 mu r square. Clear? And this is the u max. Remaining terms are pi by 2 r square. So if you calculate, 1 by 8 mu minus of del p by del x pi r to the power 4. So this is the discharge equation. This is the discharge. So this is all about the discharge flow through the circular pipe. We will next discuss discuss the pressure drop term, which is a very important, but we will discuss in the next video. Okay, thank you, bye bye.